So as we continue on with Module 4, we're going to go into now Module 4.2. We're going to continue looking at materials right here. Now we're going to talk about selection and material properties right here. So within this section here, some of our objectives are going to include material strength properties, talking about machinability and fabrication related to material selection, look at some various different metals and see how those compare, along with some plastics and composites as well. And from there, we're going to go on to our material selection charts and the process for selecting a material. So activities within this module here, we're going to take a look at some theory, discuss some key equations related to this, go through some practical applications, and then at the end, we're going to get into some actual problem solving. So as this relates back to our textbook, this is Chapter 3, our materials chapter right here for Module 4 from our ME 171 textbook. So the first thing I want to talk about here is stress and strain. First, let's take a look at engineering strain right here. So our basic definition for engineering strain we've seen before is that sigma is equal to N over our A naught right there, our area, our load over our cross-sectional area right there. Whereas we have our engineering strain here, our epsilon right here, this is equal to our delta over L naught, where L naught is our original length right there. So we have our new length, our deformed length there, minus our original length divided by our original length right there, and that's going to give us our engineering strain. Now, as a review from our previous lecture, we're going to go take a look at our stress strain curve right here. So we have a basic stress strain curve shown over here in our diagram. We have our strain on our x-axis, our stress up here, on our y-axis right here. So we can take a look and see, okay, there is our S of E, where S of E is our elastic limit. Then we have our S of Y, or our yield strength right there. And then up here we have our S of U, or our ultimate strength up there. So this is just a quick refresher from what we discussed in Module 4.1. And as we continue on to that, we can talk about our proportional limit, where the proportional limit is the stress where the stress strain linearity ends, and SE is the elastic limit, whereas the stress where the material becomes permanently deformed. So there is a difference between these two here. Your proportional limit is where the stress strain linearity, where that linear line stops being linear, when that ends, that's your proportional limit at that point there. Whereas SE right here is your elastic limit, and this is the stress where material becomes permanently deformed. So that is different for different types of materials. SY is our yield strength, and this is the stress where significant plastic deformation has then occurred. And last, we have SU, our ultimate strength right there, and this is the highest stress that is achieved. So I want to take a little bit of time now to discuss the difference between this elastic limit and a proportional limit right here. So the elastic limit is going to be principally different from the proportional limit, but the proportional limit is going to mark the end of the elastic behavior. Now this can also be described, as we've seen before, in Hooke's law. And we can say that the stress is proportional to the strain, our relative deformation, or in terms of our raw data, we can say that the load is proportional to our displacement. Now, this elastic limit does nearly coincide with the proportional limit for certain elastic materials. So much so that at times the two are very difficult to distinguish the difference between them. Whereas for other materials, a region of non-proportional elasticity exists between those two. So there are going to be certain materials where you can see that difference between those here. So we can see down here in our graph right here, the proportional limit is the endpoint, which is called the linear elastic behavior right there. So we can see this is the endpoint of our linear elastic behavior, that's perfectly straight right now in our linear region. So that's a proportional limit right there at that endpoint of what we call that linear elastic behavior there. Whereas we can see our elastic limit for these other materials right here is up a little bit further right there. So this is our elastic limit there. So again, if we look in and maybe even zoom in a little bit on our strain region portion of our graph right here on the x-axis right there, you can see for certain materials there is a difference between the proportional limit and the elastic limit, again, depending on which material we're looking at. So now we're going to take a look at a stress strain curve here for our steel right here. So for steel right here, we can see there is a little bit of a difference from different types of materials on here. We can see within this elastic region right here, it's a very sharp curve right there. So you can see our strain doesn't increase much, but our stress goes up really, really quickly until we get to our point A right here. Then we go from there, from our elastic region, into our pure plastic region after that, where we can see then we have some strain hardening going on. So we get up here to see our ultimate strength right there, and then after that, we see some necking occurring until we get to fracture down there below. So this is the basic shape of a lot of the different types of steels as far as when you're looking at your stress strain curve here. And it's going to bring up a new topic that we're going to discuss in the next couple of slides of modulus of toughness. Now, if we're continuing to look at our stress strain curve right here, for steel right here, if we zoom in at that first elastic part of this right here, we can see the strain is minimal compared to our stress right here. We're going up to almost 280 MPa over there. We're barely getting below 0.002 for our strain right there. So we can see we have our upper yield stress right here, which is right at our point A. There's our upper yield stress. And then right here for this line at B right here, this is what we're seeing right here is our lower yield stress right here, where we have sigma YL and sigma YU for our upper yield stress, and this right here, YL for our lower yield stress there. And this is going to lead us to the topic of the modulus of resilience. Now looking at our stress strain curve here, let's take a look at this now for aluminum rather than steel right here. So we can see this is a much different shape as we look at this here. We're coming up now, okay, there's our 0, 0. We go up here to our proportional limit. So there's our proportional limit right there. A piece of L, we can see that's an A, so that's right after, right, that end point right there at the end of our linear region right there. Then we can see we come up to our yield stress up here, our Y. From there, we can see at our yield stress, if we follow this back down, if we were to unload that at that point there, we can go back down. We can see a 0.2% offset right there, and we have permanent deformation after loading once we've achieved that yield stress right there. So if we come back down, we can see there is a permanent deformation after unloading our sample. So now we've taken a look at our stress strain curve for various types of metals. We've looked at some steels, we've looked at some aluminum now. What about a polymer with our stress strain curve here? So we have our basic stress strain curve, straight on the bottom. Our epsilon is equal to our change in length over our original length. We have our stress over here. Our sigma is equal to our load over a cross-sectional area. Now let's just talk about these in the general sense right here. If we have a more brittle material, what do we notice on our stress strain curve here? So for a more brittle polymer over here, we can see this is a very steep curve right here. There's not much strain. It just goes up straight to failure. It almost stays in an elastic region the whole time and then just fails. Then we have over here limited plasticity right here. So you have a material that's like this here. It's still pretty brittle, comes up right here, not much plasticity to it, comes up, still does a little bit, gets out of that linear region, goes into the plastic region right there, and then pretty much fails right as it gets to our ultimate strength right there. Then we have some cold drawing down here, so we can take a look at this here. We can see our general shape here for cold drawing, and then again for viscous flow down right here. So this is just a good chart to reference back to. If you're looking at different types of plastics and they tell you, hey, you're dealing with something with limited plasticity, you're dealing with something that's brittle, you're dealing with something with cold drawing or viscous flow, that you can come back here, get an idea, okay, well, what should my graphs look like for my stress strain curve? And this is a great place to get that reference. So another material I want to discuss briefly right here is ceramics. So we're taking a look at stress strain for ceramics right here. A lot of times we may not be dealing with tension, we may be dealing with compression, and that's what we see down here for our sample right here. We can see I have our compressive load F right here, our original length L right there, and our original cross-sectional area A naught. So rather than putting this in tension, we're going to be putting this into compression. So we can see we have our compressive strength up here, we apply our load, and we see our stress strain curve over here, and our strain on the bottom, our stress over here on the y-axis. As our stress goes up, see, it stays pretty linear right up to there until we get to our compressive strength right there, our sigma sub EL right there, and then we can see, start to see here as it kind of crumbles and falls apart as we're going down here. Now, for concrete, this is a tricky one. I've done a lot of research work with concrete in the past, and there has been a few instances where we've actually wanted to do tensile testing. We wouldn't want to just see the compressive strength right there, but we were interested in how it would fail in tension, what loads it would fail in tension. So what we did is a lot of the work we did with bridge decks. Now with bridge decks, you have rebar embedded in the concrete, so that's exactly what we did. We made some test specimens with various types of concrete that we then put on a tensile testing machine where we gripped the two ends of the rebar and pulled it at a slow rate, and then took a look at our tension testing and our load versus deflection, and in turn our stress strain graphs related to that there. So that's not very common. It was a very specialized case for us because we wanted to see there were certain portions of the bridge, certain girders and supports that are put into tension. We needed to see how the concrete would react in tension and not just in compression here. So now I want to talk a little bit about our material properties. Now, when we're talking about material properties here, we don't always have the luxury of being able to go in and run a tension test, get that information for our stress strain curve right there. Sometimes this information is obtained from the manufacturers. And a lot of the sheets from the manufacturers, some of these values are listed right out, or in some cases they will give you the stress strain curve and we can do what we've done before and fax the information out. But a lot of times it's just a table where they give you these values here. One of the values that they give us right at the beginning here is our elastic modulus or our Young's modulus there. Another piece of information for material properties we often see in these charts is Poisson's ratio and our shear modulus as well. Now we can also see down here that these are all for the linear elastic region of our stress strain curve right here. They're all related back to that linear elastic region. So let's take a look at each one of these here. So if we want to talk about our elastic modulus, Poisson's ratio, and our shear modulus right here, our modulus of rigidity is also known as, what we need to do is we can use equation 3.14 in our textbook right here. And this relates all three of these together. Now the thing to think about with this here is that you need to know two of these three in order to solve for the third one there. So if you only know one of these, we're going to need to find another relationship in order to solve to find out the third one as well. So you really do need two of these or a relationship or equation that relates it to get you the information of the other one as well. So we see here we have 3.14, we have G, or our shear modulus, is equal to our modulus of elasticity divided by 2 times 1 plus Poisson's ratio. Now we can rearrange this, we can solve for Poisson's ratio right here, and we see the Poisson's ratio is equal to our modulus of elasticity divided by 2 times G, our shear modulus, minus 1. So another piece of information that we can infer from our stress-strain curves here is how ductile or brittle a material is. So we can take a look at this ductile and brittle behavior, and this will lead into our topic of energy absorption right here. So we take a look and we see a more brittle material. Again, we have that steeper line on our stress-strain curve here, and it pretty much goes right out of that elastic region right to failure right there. Whereas we see a more ductile material, we have a more soft curve like this here, where we can see there's not much of a linear region here. It gets into the plastic region, then you have your strain hardening, then you have your ultimate strength, then you have your necking, and then you have failure at the end there for more ductile materials. This is something more of a steel as compared to a aluminum or a plastic down here. So the next topic I want to get into here is energy absorption right here. So in some cases, some parts are maybe designed more on the basis of absorbing energy rather than withstanding load. So a lot of times we're like, what is the maximum load it can handle? Well, that's not always the case for every type of product that we're doing. Sometimes we're really concerned about how much energy it can absorb more than that ultimate strength right there. So within this here, this energy is going to involve loads and deflections, which makes sense. We think back to our raw data, again, if we're pulling a tensile test right here, what are we collecting? We're collecting our how much load there is that increases at whatever rate we're pulling it at right here, and what our deflections are. Now from our load and our deflection raw data, we can then go ahead and get our stress and our strain curves right here. So we have our stress up here on our y and our strain down here on our x-axis right there. So the strain scale on this one here, we just expanded out this a little bit more. So we just kind of stretched out that strain axis right there on near the origin for a little bit of clarity over here. And we're looking at this region right here. So there's our SE and our SY and our SU. So we have our elastic region, our yield strength, and we have our ultimate strength right there. And we can take a look and zoom in on that area in that elastic region. So as we continue on this topic of energy absorption right here, the next thing I want to discuss here is our general equation here and our relationship for our modulus of resilience, our R sub n. This is the energy absorbed up to the elastic limit or our yield strength there. So we can come over to our graph. There's our stress strain curve over here. We see, okay, there is our yield strength right there. There's our elastic limit right there. If we just go up to our elastic limit, we can see we have down here, okay, there is our value over here of our strain right there, which is our S sub E, our elastic limit, divided by our modular elasticity of our slope right here coming up the side of this right there. Now we come up with, related back to equation 3.8 in our textbook, a general equation for our modulus of resilience right here. So our R sub m is equal to 1/2 that S sub E right there, that elastic limit, times our epsilon sub E right there, our strain, and this is equal to, we can rearrange this, put some substitutions in. We can see here this is 1 over SE times, if we put epsilon sub E by our SE over E, which is exactly what we get from our graph right there. Plug that in there, we can see now we have an SE times an SE, which is SE squared. So we now have SE squared right there all over, that 1/2 comes right through, our E's right there, our 2E, which leads us into the final solution right here for equation 3.8 from our textbook for our modulus of resilience. So now as we continue on with energy absorption right here, we want to discuss our modulus of toughness, our T sub m, or the energy absorbed up to fracture in this case here. So we're talking about our energy absorbed up to fracture right here. We can now see this region right here. There's our fracture region like that there. So now if we're talking about this dotted box right here, this rectangle right here we have is a relationship shown in equation 3.9, where our T sub m right here, our modulus of toughness, is equal to the integral from 0 to E sub f right here. So there's our 0 to our E sub f right there of our stress, or sigma, times delta, or d epsilon right there for our strain right there. So this comes from equation 3.9 in our textbook right there. And we can also say this leads into 3.10, which is equivalently equal to our SY, our yield strength, plus our ultimate strength right there, divided by 2 times that E sub f. Now E sub f is our strain at the fracture right there. And again, our S sub y is our yield strength, and our S sub u is our ultimate strength, as we plug into this relationship here for our modulus of toughness from equation 3.10 in in our textbook. So going back to our brittle materials here, one thing to consider here is that brittle materials are going to behave much differently in compression as opposed to tension right there. So sometimes we're talking again back to the concrete that I was talking about there, how I said there was a couple instances where we actually embedded some rebar into the concrete there so we could take a look at what the tension did on our samples for different types of concrete as compared to what the compression test, the standard compression tests were doing. And this becomes important because these materials, such as concrete there, these brittle materials are going to behave much differently in compression as opposed to tension. We can see an example of this in this chart here. And why this is important, if you think about, again, for structures, there's a lot of parts of concrete structures that are going to be in tension and in compression. And it's important that we understand how these different mixes, different grades of concrete are going to react for these different scenarios. Maybe there's a better type of concrete, a different type of reinforcement we should put in that concrete if we're going to have something in tension rather than compression, or vice versa. Now another material, brittle material here we might want to take a look at is our gray cast iron here. So I've included here just another chart on our stress strain curve right here where we have our stress in KSI and we have our strain in inches per inch for this this gray cast iron. So again, how does it compare in compression versus tension right there? So these are some other important tests that may be crucial to run depending upon how you're utilizing the cast iron in your part, your machine, your product, whatever it is, your system as a whole. Is it putting in tension? Is it putting in compression? And then not only that, but where we want to go from here is not just compression and tension, but is it a static loading? Is it dynamic loading? Is it cyclic loading? How is the life cycle testing of it? And compare this for both our brittle materials and our more ductile materials as well, and decide what's going to be a better fit, which is going to last longer, which is going to be a better material for you. So this all ties right back into that material selection. You may not be saying, I definitely want this exact material. You might be saying, do I really want to go brittle or do I want a more ductile material? And come up with that first and decide, okay, yeah, for my application, it makes a lot more sense. I'm seeing a lot more tension right here, and I see the way concrete reacts in tension right there. That's not my best bet right here. Whereas if I had a compression system, maybe these concrete blocks at the bottom here, which held the whole structure up, might be a little better fit for something like that. Same thing when we're talking about cast iron. Maybe you want to go with a stainless steel rather than a cast iron for a multitude of reasons, whether it's in tension, whether it's in compression, where it's going to be, environment, all those factors come into play. But again, this is another one we really do want to take a look at our stress strain. Now that we've seen the difference in behavior between brittle and ductile materials, you can look at those stress strain curves and decide, is this a good match for my application? So one thing to also consider as we're looking at this ductile and brittle behavior within materials here, that many materials may exhibit both of these behaviors to some extent right here. And this comes into play with our composition, temperature, and strain rate. So things are going to behave differently with different compositions, different temperature ranges, different strain rates. Things of that become important and kind of can change the way a material will behave. So we take a look at this here. So we talk about composition first. So we're talking about composition right here. Here's some different types of carbon contents within steels. This is our basic stress strain curve right here. What we can notice here is along this curve, this is going pretty linearly right there for all these different types of steel. So our modular elasticity doesn't really change much there. What does change is we kind of peel off right here with our strain. So these softer steels, the 0.1% carbon right here, see it only goes up to around maybe like 32, 33 KSI, and then we start to see it hit our yield strength right there, come off, and then go to failure over here before it even gets to 40 KSI. Whereas on the other hand, we might see a spring steel up here with 1% carbon right here, 10 times as much carbon in it right here. We can see it still follows the same modular elasticity, the same all the way up there until we get to now like 162 or something. We start to see yielding going on, and even then it still continues to go up right there before we get to failure around 175 or so KSI. So this is something to consider, is even the composition, the makeup, the percentage of carbon in the steel you're using could be beneficial for whatever your product is. So if you have a product where you need something to go a lot higher stress right here, and you don't care that it stretches more before failure, you're just really concerned about that maximum stress right there, well then maybe a spring steel is better. Whereas if you can't have much deformation at all, or no permanent deformation, but you know your loads are going to be lower, your stress is going to be lower down here, maybe you want to go with a softer steel down here like that, or a structural steel, something like that there. So depending on your application, your product, knowing that the difference here in our composition of the material could be very crucial. So still going to be a steel, but just maybe your percentage of carbon changes. So let's take a look at this composition for our aluminum alloys now rather than steel. So you can see we have a 7075 T6, 2024 T3, and a 6061 T6 over here. You see on our y-axis we have our tensile stress right there in KSI, and we have our strain on our x-axis over here. You see it stays pretty linear, and there's identical for all of these. This elastic region there. What we can see is our 6061 right here, aluminum alloy, kind of comes up right about 42. Then all of a sudden we see the yielding coming across, and then hit our ultimate, and then down to failure right there. So that maybe If we look at this over here, is that the tensile strength that's acceptable for us there? Or do we want to go a little bit higher up here? We want something over 2024, but we might get a little bit more strain out of it here. All decisions you have to make in this material selection process. The one thing to notice is just that modular elasticity is not always going to be enough information for you. You're going to need some of these other material properties to help you make those decisions. So another factor that comes into play that we talked about here, not just composition, was also our temperature. How does temperature affect our material properties? Well, we can see here, if we just go at room temperature right here for steel, cooling steel right here, right at room temperature, if we cool that there, there's our stress strain curve right there. Pretty mellow right there, like that, what we expect to see. But all of a sudden, we're going really cool at negative 253 degrees Celsius. All of a sudden, you see this is a lot steeper going up right here. And so far, we see these different shaped curves, even at negative 196 and negative 79, if we're talking about extreme cooling of this steel for this here. So as we continue on with our temperature discussion right here, let's talk about heating rather than cooling of our steel sample right here. So we look again at our stress strain curve right now. We say, okay, if we're at room temperature, we have this basic shape right here. Then if we increase it from there to 204, we have this next curve. Then we go to our 316 and change this slightly, and then to 427 and change this slightly there. So heat treating this steel is also going to affect its material properties right there. So we can go back, we can get our information from our stress strain curve. What is our yield stress? What is our ultimate strength? What is our failure? What is our modular elasticity? All that information that we can get from a stress strain curve, we can see that how this is going to change. But just even looking at the graph right here, how heating of the steel is going to change those material properties. So the last thing we talked about here that could affect our material properties is our strain rate right here. So the faster rate of testing, if we pull this at a faster rate here for a tension test right here, this may result in more brittleness right here. So if we see here, if this is a faster rate right here, we're going at our E.3 as compared to our E.1, you can see this exhibits now more of the behavior of a brittle material than if we pull it at the slower rate down here. So again, we see that our E.3 is higher than our E.2, and our E.2 is still higher than our strain rate down here at E.1 right there. So again, you can see even in our visual right here between those different strain rates, we can see as this gets faster right here, up to our fastest right there, or for 3, this is going to make the material, the properties right there, much more brittle right there. We can even see that in that curve. So as we move forward with our stress strain curves, we want to see what happens in reality. Typically, we've seen all these curves right down here that are nice and pretty. We see we have our strain down here on our x-axis, our stress up here, and our y-axis right there. We can see we have a nice easily defined, perfectly straight line there. The slope, which is our modular elasticity right there. Come up and it's an easy spot to feed with this bubble right there. There's our elastic limit, dead on 36, and we can see there's our yield strength right there, 39. Then we have our ultimate strength up here at 66, and we have our fracture right there, clearly defined. So this is what we're used to. What happens in reality? So I take a look at this video right here, take a look at this link here, check out a little bit more of the reality side of things when we're talking about some of these stress strain curves. So one thing to note is we're looking at some other results here. This was a great video, and they really did show us the whole application, right from the tensile test, the specimen. They talked all about all the different parts of the tension test there and how we got our results. What we'll notice here is we're always not going to see the same exact units that we're used to our textbook being in. So just because we're used to, okay, SE is this and SY is that and this is SU, that doesn't mean that's what it's always going to be. You're going to go into other courses, other textbooks. You're going to go on to grad school, go get a job in the field. You may be doing some research on your own, looking things up, and you're going to see different variable names, and you need to understand how those still all relate together. So that's why I think it's great to look at these different videos right there, and I think a lot of these tensile testing videos are pretty interesting and fun to watch. In general, anyways, you get some great ideas on some different types of test rigs and applications and all that stuff there, and it also gives you some background information all from using this type of material. Maybe this is a good strain rate that I should use for this, or this is a good data acquisition rate I should use there. But I would go ahead and take a look at this and follow some of the other links that pop up often for these different types of tensile testing and our stress strain related curves right there, and take a look at some of these different variables that they're going to be using and how they relate back to what we're used to seeing for the typical variables in our textbook. So tying in with that, we want to really look at each of these. What, not just remember, okay, that's where my SU is. Well, what is my SU? What does that actually mean? Same with our SY and our SE, our elastic limit, our yield strength, our ultimate stress right there. Well, what happens? In this case here, let's just take a look at SU right here. What happens after this ultimate stress is reached? Well, we can look at this and we really think about it. Don't just take the graph for granted, but actually look at what that graph does and what information can we draw from that there. So if we take a look here, well, we hit our ultimate stress right there, and we can see the stress decreases as the strain increases. So our stress continues to go down from that point after the ultimate stress is reached, but our strain, we can see down here on our x-axis, still continues to increase as well until we get out here to our fracture point right here where we can see our strain is 1.5. But from SU right here of a 66 KSI for our stress and a 30 for our strain, we go all the way up to 150 for our strain before we see failure. This whole time, the stress is dropping back down below. So think about this here, the matrix of the material is also stressed so that it begins to fail, to deform at the molecular and atomic level in an irreversible deformation. It begins to deform by thinning the neck. So this is again what we call our necking region right there because it is deforming and thinning the neck right there. So it's weaker because of that. So once you've gotten to this ultimate stress right there, at the top of this right there, what is going to happen? Well, it's going to get weaker after that point. To the point where if you achieve this in a part or a product or something, it's not going to be as strong. It's not going to be able to withstand the loads it was before, the stresses it saw before. It's going to be a weaker part, and it's going to continue on that necking as it goes down until it finally reaches failure. So it might be slowly creeping down after day as you add more and more stress to it until it fails on you. Maybe you don't want that to fail. Maybe you only want to take, when you're designing your product, so it never goes above a stress over here, so you never even get to even your yield strength there. Maybe you always want to stay in your elastic region. So those are things to think about, is what these actually mean for these values, not pulling off chart like, oh yeah, no problem bringing anywhere near that with mine. Well, maybe not. What's going to happen with life cycle testing? Is it going to become weaker? Is that something that's acceptable for your design? So what we have here is a stress strain curve for our hot roll 1020 steel. This could be any type of material, but for this example here, we're just going to look at 1020 steel. And we look at this here and we see we have our information. We have our elastic limit of 36 KSI. We have our yield strength 39 KSI, our ultimate strength up here of 66 KSI. And what we can do is for each of these, we can drop down and take a look at what our strain is. So we can look right down our x-axis there. So if we say, okay, for our elastic limit right here, take a look at that right there. We can drop that down and we see that our strain right here, if we could zoom in on that portion of the graph, would be over there at that. We drop straight down, go through our strain right there, and we end up seeing a 0.012. It's right next. You can see it's almost right on that axis there. So we can see that's our strain right there. It's a little bit more evident here if we talk about our ultimate strength up here, our strain right here. If we drop right down that line there, that's at 30 right there. So therefore, there's our 0.3 right there. Again, this is in percentage right here, so 30%, there's our 0.3 right there. We can also see we can get our area ratio, our R value right here by dropping down to this graph right here, and see that's at rate of 1.3 for that there. And our AR, or area reduction right there, is at about 0.22 right there, so that's what we write down right there. So we can do the same thing at our fracture over here. Okay, our strain at our fracture is at 150% or 1.5. Our R value is 2.5, and if we go all the way down, our A sub R is at a 0.6. So this is another way that we can present some information where we can back some more material property information for different types of materials where they give us this type of stress strain curve. So as we've been looking at our stress strain curves, we've discussed a few different times the necking region right here after that ultimate strength of what's going on. Afterwards, we get into that necking region right there. We can look at a practical sample right here. We have our original length L naught. We have our deformed length L over there. This is for a constant volume. We can see the necking region right there. So let's take a look at some governing equations within this here. So what we can do is we see that, okay, our A naught, our initial cross-sectional area, times our original length right there is equal to our final cross-sectional area times that original length plus that change in length, our delta L right there. Now what we can do right here with this relationship is we can do a little bit of a math trick here. We can see that L naught over L naught is 1. We can multiply through that, multiply this delta L by a 1 right there without changing anything within that there. The reason we can do that is then we can then simplify this down and realize, okay, if we do that there, then we have an L naught that we can pull out front right there. So this is now equal to our final cross-sectional area times the L naught times, once we pull that out, a 1 plus delta L over our L naught right there, which then we can rearrange a little bit more, and we can see that this is equal to our final area times that initial length, and this is a 1 plus, and our delta L over L naught is our strain right there, our epsilon value right there. So we've reduced that down from those relationships right there with just a little bit of a math trick of multiplying through by 1. So the next thing I want to discuss here is true stress. What is true stress? Well, stress with change in the cross-sectional area right there, our true or our normal stress right there. So we can see this as a sub T right there. So our sigma sub T is our true or our normal stress right there. And this is equal to our load divided by, now we have our final cross-sectional area right there, not our initial cross-sectional area there. So that is the difference between our stress and our true stress right there. Where what is AF? Well, AF of our cross-sectional area is our initial A naught right here over 1 plus that deformation of our epsilon value right there. So if that's our value for AF right here, we can take this relationship right here, plug it back in over here, do out a little math, and we see that our normal or true stress is equal to P over A naught, which we're used to. That's what we're used to seeing for our regular, for our engineering stress right there, just our sigma. But now for our sigma sub T, or our true or normal stress right there, it's that times 1 plus our epsilon value. So again, if we're used to this just being our stress right there, we can replace our P over A naught with just our sigma right there. So we can see that our sigma sub T, or our true or normal stress, is equal to our sigma times 1 plus our epsilon right there, where we're calling 1 plus our epsilon our R value right here. So now that we've discussed our true stress, the next thing we want to take a look at here is our true strain. So what is our true strain with this here? Well, this is the change in length divided by the length existing immediately prior to the last small strain step. So it's a little bit complicated in words there. What this says right here is that our E sub T, or our true strain, is equal to the summation from L naught, our original length, to our final length, L sub F right there, of our delta L over L right there. And this is equal to, if we want to do an infinite sum of these right here, the integral from L naught to LF of dL over L in order to get this true normal strain. So we can say that there, we do out our integral right here, do out some calculus. What is the integral of L dL right there? Well, this is equal to the natural log of L over L naught, which is our final length over our initial length right there. So we can say, okay, let's do that out there. Well, L over L naught, that's going to be our R right there, where our R value is our 1 plus epsilon right there. So this is equal to our natural log of 1 plus our strain right there. So our true strain right here, or our normal true strain, is equal to the natural log of 1 plus epsilon. So with our true stress and true strain, we can come up with a different type of stress strain curve that we see here. We have our true strain on our x-axis down here. This is a percentage in a log scale right there. And we have our true stress up here. This is KSI on a log scale as well there. When we're looking at this as a log scale, with these true stress and true strain, it does look a little bit different right here. We see we have these different regions right here. We have our elastic region. So we can see go up to there to our elastic region. Then we have our transition region up to here. And then we have from there our plastic strain, our strengthening region up here until we hit our failure right there. So this is a different way to look at it using our true stress and true strain on a log scale right there. So we can see we have our elastic region right here. So our sigma sub T right here, our true stress, is equal to our modular elasticity times our epsilon sub T, or our true strain right there. So for this case here, if we do it that, this would be the slope of this right here, which would be our E is equal to 30 times 10 to the third KSI. And again, this is just for the particular example of our hot rolled 1020 steel. So we can see there is our general equation right there, sigma sub T, right off our graph right there, is equal to our modular elasticity times that epsilon sub T, or our true strain. Now we can move on to our transition region over here. And what we can see in our transition region right here is we have our sigma sub T is equal to our SY right there. So this stays right at that SY, our yield strength right there. And this is giving to us, as in this case here for our 1020 steel right here, 39 KSI. So pure plastic behavior right there for this case right here in our transition region. So now we move on to the last region right here, our plastic strain strengthening region. So this is where our transition region ends right there. Where again, we had our sigma sub T is equal to, in this region right here, our S sub Y, 39 KSI, constant throughout that whole transition region. Now we see it increasing right here, and increases right here that our sigma T follows the relationship from the strength hardening exponent right here. Now we see that right there, our M value right there. So sigma T is equal to our sigma naught times E sub T, which is our true strain right there, to the power of M. Now for our case here, we can see that our M is given to us in this region here for our hot rolled 1020 steel of 0.22, and our sigma naught right here is given to us as a value of 115 KSI, so we can plug in those two values there and there in order to get our information for our true stress and our true strain. So as we continue on with the topic of material selection right here, we're going to talk about how this is kind of an iterative process when we look at this here. So if we see, when we start out with any of these design projects we just talked about at the beginning of the semester right here, we're talking about this need, the market need, a problem that's been defined, whether this is from your client, whether this is from a funding agency, whether it's something that you're developing yourself, and you saw, okay, this is a market need right here, and this is the problem definition that I'm going to follow. Now, Once you have that information in front of you, the next step is to continue on to the concept, exploring these working principles. So what is your general concept? What are your ideas for this right there? So there's two paths that we can think about considering that in terms of. We can look at that in terms of the material data needs and the process data needs. Now, if we're talking about the material data needs, we're starting at the higher end right here. We're talking about the family. So when we're talking about material needs, when we're talking about our concept right here, we're talking about what type of material, what choice of material. Is it a metal? Is it a ceramic? Things like that. Whereas if we're talking about the process data needs, this is again, we're at the higher end right here. We're thinking about, okay, is it casting or is it molding at this point? What is going to be the family of that process that we're going to use? Now, as we get down further, we kind of narrow down our concept and we ask ourselves these questions. Okay, yeah, I think it should be a ceramic, or I think we should do some casting for that. Then we need to get into more detailed information with each of those. So that's where we get into the embodiment of the design right here in our selection process here. We define the general layout and our scale right there. So once we know kind of that layout and what sizing we're going to do and dimensioning and things like that, we can then get on to our class. So a little bit more specified here. So we're talking about material over here. We're talking about what class is it. Okay, we decided it was going to be a metal. So what type of metal was it going to be? Was it going to be a steel? Was it going to be a nickel alloy, aluminum alloy? So we're getting into that class of metal. Not completely dialing in on exactly what we're doing yet, but what class of metal are we going from here? Now, if we're talking about our process needs over here, this is where we said, okay, we're going to go with casting, but what type of casting should it be? Well, is it die casting? Is it sand casting? What other casting process could we use there? So now we've considered what casting process, we've got in the embodiment, so now we'll get into the details of this right here. So within the details is we're optimizing it ready for manufacturing and assembly right there. So that's where we get in, okay, now we decided to go, what single choice of material did we want right here? We decided to go with, was it an aluminum alloy? Did we want the 6061 for the aluminum alloy, or did we want to go with a steel and it was the 304 stainless steel that we need to go with? We're going to pick that one material that we're going with here. Now we're talking about that one single choice over here in the process side of things. Okay, what type of casting was it? Okay, it's going to be a die cast, but it's going to be a pressure die cast that we're going to use right here. So then once we have all that information, we know exactly what type of material, we know all the detailed information, we know what process we're going to use for this, that's where we can go into our product specification. So as we're continuing to discuss material selection, I like this chart below here. This really helps give us a visual of what's going on, kind of our steps along the way, and seeing it's not a straightforward linear path from one thing to the next thing to the next thing. Sometimes it is an iterative design where we need to go back, re-identify a better material because it didn't quite work out. And that's the reality of the design process. You're never going to get it right the first time with your first cast because you did your research perfectly right, and yep, that's what it was going to be, it's perfect, we're good. No, it's going to be an iterative process. You're going to test it out on material and realize, oh wait, no, I would really like something more like this, or these properties aren't quite what I thought they would be, or people are going to use this object or part in a different way than I intended them, so therefore I'm going to need to go back and do some changes to that. So we'll start over here at the beginning here. We identify the characteristics of our application of our design right there. From there, we want to identify the component specifications that we discussed a little bit there. From our component specifications, we can then identify the required material properties. So that's we can go for those properties, well, which one has those properties? We can go back to our charts, we can go back to those stress strain curves and everything we discussed at the beginning of this lecture here, once we know what those required properties are. From there, we can select potential. We call this potential right here, material candidate considering. There's a lot of things to consider in this. We've already talked about the properties and those we consider, but what other things are there to consider? Well, there's cost, there's availability, there's also machinability, all those things, all those factors. What is your budget? What are your needs? What is your environment? All those type of things come into play right there. So then we come down there and we see is we then start the fabrication of our components. So if we start the fabrication of our components right there, well, we might immediately say, wait, no, we need to go back up here and try a different one here. Because that did not quite work right there. And like, wow, there's not really a good selection on these potential materials. Maybe we need to go back one step more. So we follow, instead of going up here to this, we then say, okay, well, now we need to go back over here and up here and identify the required material properties, look at those again. Maybe some of those need to be tweaked. Well, that didn't quite work either. Maybe we need to go all the way at the beginning and identify some of the component specifications, maybe something was a little off there. Then we go back through this process again down to manufacturing, and then we might get to here, and then, oh, that still wasn't right, back to here, back to this. Slowly going through this process until we finally get over here. Now we're at the verification and testing evaluation. So we made it through fabrication, everything worked out well for the fabrication portion of it, but now we need to do our verification, testing, and analysis, and from there we might say, wow, that was not even close to what we needed for our material properties there, for our failure rate, for our life cycle testing, whatever it is. So then we might, again, need to go back here and figure out, okay, what required material properties are there that would fit that, and then select a potential, refabricate that, and maybe there's more issues with fabrication, and you could go back and forth through all those until you finally come down here and flush one out that passes your verification and evaluation testing right there, and this is therefore going to be your best material. So this is not a straightforward go here, go here, go here. There's a lot of looping back and around and forth again until you finally do converge on that best material. So another thing to consider in table 3.3 is a great way to summarize this is the characteristics of the material. So we're not just talking about the mechanical characteristics that we're used to here from our stress strain curve, where it's the strength, elastic, modulus elasticity, hardness, Poisson's ratio, damping, tensile test, all those things, fatigue. Those are great, and we do need to consider those, but there's other things as well. Physical properties, are we concerned about density and the electrical, magnetic, optical, conductive, anything like that? Can it be near flames? Is there a melting point it needs to be? Is there specific heat? Is there absorptivity requirements all within those things there? And these are things that may be specified by the environment you're using the product in, by the funding agency that is giving you the information, by the client who knows what is going to be a bigger part of another system right there. So those right there, then you have your chemical ones. Is there corrosion involved in the saltwater environment? What is the composition of it? Is there any issues with certain types of materials in that composition? What is the stability of it right there? All those things can be used when there are other chemicals. How do those react? Are there any environmental factors? Does it need to be biodegradable? All those come into part with our chemical properties there. Then we have our dimensional properties. This is when you start getting our modeling there. Does it need to fit in a certain area? Does it part of another system? Does it need to fit in and mesh with something else? Is it compatible? What is the profile? What is the surface finish? What is the stability? What are the allowable tolerance? All those are your dimensional properties there. Then your manufacturing process right here. So this is what we talked about. Are you casting it? Is it heat treatable? Is it hardenable? Is it formable? What is the machinability of it? All the stuff with how you're actually going to machine it. So go back to the other process, we're comparing those back and forth with each other. That becomes important. Looking at those at the same time, what material to select and how you're going to machine it all come into play. Then cost. Cost is one we don't like to talk about because that may steer us away from the best product that we can get that fits all the criteria, but it's very real. So cost is something like the raw material cost, the quantity required of it. So maybe you get a bulk discount, the predicted life service of it, any additional fabrication. Certain materials have additional costs because it takes a special type of fabrication to work with those. So all those fall under our cost material characteristics. And last, legal. Is there any code compliances, environmental issues, health issues, disposability? Is it recyclable? Liability stuff because you hurt on it. All those things come in, and this is where you really need a specialty branch within your engineering services or division or company that has that knowledge, or hire somebody from an outside source, a compliance engineer potentially, who can take a look at this and let you know what this information may be needed for that there. So all of this, not just your mechanical that we're discussing here, but all of this comes into that material selection. We're talking about the characteristics of these different materials. So I just want to briefly mention Appendix C in the back of the textbook here, Appendix C19. This is material classes and selected members of each class right here. So this isn't all of them, but if you're looking for, okay, what are some engineering alloys right here, some engineering metals and alloys, well, here's the members, here's the abbreviation for them there. So it's like you might see something specified. It needs to be a nickel alloy. What is that? Ni alloys, okay, it's a nickel alloy. It needs to be tin alloys. It needs to be a W alloy, okay, that's tungsten right there. So all of those right there, they may be specified, or maybe something to consider. If these are some of your criteria that you need to follow, if it needs to be a ceramic, what are your options for ceramic? What do we see for our abbreviations for those if we're getting them from tables and things of that nature? Understanding what these are. So this is a great reference to come back to when we're taking a look at these material classes in the back of your book in Appendix C19. So we've already showed a couple different ways to go through this material selection process. Here's another chart here. This isn't one of my favorites, but if you need to do a quick one to get a final material choice right here, this is an option that you can go through right here. It's just a different way of expressing those same type of steps. But I like the ones that really show the iterative process and this, and that it's not a linear, straightforward function. But this is another quick way, an easy visual to look at this here. So you have all your materials here. You need to make a selection for a final material choice at the end. So the first step is to translate. So translate design requirements. What is, again, stuff from your client, stuff from the funding agency, stuff from what you know you need for your personal project you're developing here. So you express as a function. What are your constraints? What are your objectives? What are your free burials? You're translating all of these design requirements down from there. Now, once you've done that and translated the design requirements, you can then screen using your constraints right there. So once you've identified those constraints, you can screen using that. So then with this, what you can do is then eliminate materials that cannot do the job. So you say, okay, I definitely can't use wood. I can't use plastic. I can't use anything that's that has magnetic things like that. So you can eliminate materials right off the top, so narrow down your search. Then once you narrow down your search, you want to rank the remaining ones there. Find the 3 materials that do the best job and rank them there. And then from there, do your documentation, so seek documentation, research this family history of the top-ranked candidates, and do your due diligence with that there. Find good sources for the documentation and do that research to come up with your final material choice. Now, the way I like this here is that this would be done prior to using some of those other processes we use there. So we're not just blindly throwing other materials into there, but you could have a good list that comes out of this here. Even after you've done all your research and you've selected these best documents here, or best materials here, you can come within this final choice with that and then go through some of the other material selection processes now that you've kind of down selected from the list of all materials, kind of eliminating materials that aren't going to do the job for you and coming up with this final list of your material choices. So another good chart we have in the back of our book, which is a great place just to poke through in general for some of this information, is the typical uses of plain carbon steels. So we talked about the percentage of carbon earlier right there in one of our charts. Well, what are some typical uses for these different percentages of carbons where we see them in realistic applications? We're talking about these lower percentage carbon ones, or you might see this in rivets and wired and cold drawn parts, or as we get up here to our higher carbon content ones up in here towards 1 and above, we got springs and knives and drills and taps and machining cutters. So that'll kind of give you an idea of what are you designing? What part is you're using? Is it similar to a gear and a shaft? Is it more of a shovel or a tool that you're building with this? You know, and then you get an idea of like, yeah, this should be a little bit more the type of steel that I want to use if I'm developing a new shovel here, or a new trowel or something like that. Yeah, I want to go with a carbon content 0.7 to 0.9. Or maybe if you're like, no, I want to design some new rivets down here, I need a really low carbon content here for that application. So this is a good chart to quickly give you an idea, compare what other people are using for typical parts for their carbon content, and look at that in your comparison when you're down selecting your materials to come up with a list for the material selection. So in Appendix C1, this is similar to some of the lists you might get from a manufacturer, much simplified down here and even less information you get from a manufacturer typically. And this is for a whole array. So normally if you get it from a manufacturer, you get it for their product and give you this information. For this one here, we're just showing some common metals and what some of the more popular material properties of this. We're talking about modular elasticity, modular rigidity, Poisson's ratio, our weight, density, our coefficient of thermal expansion, thermal conductivity, and specific heat. So if those are any things that are considerations, even for down selecting or final selection of a material, this appendix right here, C1, gives you a good idea. It also lets you know, like, hey, maybe there's a copper here that kind of meets some of the requirements that you need, but not quite. You know, is there a different version of this copper from a different manufacturer, or for a different type of steel, or a steel alloy that you could use from a different manufacturer that you could go to and say, okay, yeah, this is kind of where I want to head, but I want to tweak it just slightly. Which company, which manufacturer releases something with some slightly different material properties? So another thing to consider, and again, another chart, another flow chart here, tree diagram, whatever you want to call it, for material selection. One thing, though, I want to bring this up for is because decisions have multiple answers. And again, I keep saying this over and over. There is no one straightforward, this meets this, this meets this, this meets this, it must be that. It's not necessarily like a straightforward math problem there. You're going to have multiple answers. You're just trying to find the best fit that meets all of your different constraints. So you have all these design requirements here. You have your required shape. You have the process that you're using. You have the material right there that you're going to select. Well, what is the cost of that material? How do you process it? What is the ecological impact? What is the required property profile? And these kind of all back and forth and tie in together, and they depend on each other, and you can finally converge on a final choice. And even then, like we saw before, once you do your testing and analysis and life cycle testing and all that, maybe that's not great. You need to go back up and try a different material there and double check everything. Does it meet your design requirements and all that? And yes, you're kind of going through what are your requirements, what are the constraints, then your choice, then what are the consequences from that choice, your impacts and costs, and then your decision right there. So yes, in a sense, you can think of it as a linear process in this way right here, but you might get to that choice and find out that these consequences are unacceptable. So you got to go back up and double check your constraints, and is there something that's different there, and does it still meet those requirements? And you make a new choice and go down through, and maybe that has some bad ecological impacts, so you go back up again. So again, it is an iterative process that you need to go through with material selection, even if you're thinking requirements, constraints, choice, consequences, decision. It looks like it's a straightforward process. Really, you have a lot of this going on, and there are multiple answers for all of